Hello, my name's Mike Chambers and I'm an AI ML specialist developer advocate for Amazon Web Services. And you would have to have been living under a rock for at least the last 6 months not to notice a massive conversation starting up around generative AI. So this isn't just now a conversation for particular data analysts and data scientists. This is now gone into the general conversation. Everybody, even my dad, is talking about generative AI. And so this presentation is a builder's guide to generative AI. And just to make sure that we're all on the same page and we're all talking about the same thing, let's look at a couple of quick examples of generative AI. Yes, all of these images have been created using a text-to-image model, something where I could type in some text, for example, a dog wearing some glasses and a hat. Yes, I typed that, and it produces this image. Images that basically haven't ever been created before, created from text. We've also all seen chatbots and text-based generative AI, where we can ask questions, for example, and get some meaningful answers out of these systems. These really are quite incredible tools, and we're going to be talking about the technology behind these tools in this presentation. So let's take a quick look at the agenda. We're first of all going to talk about the road to generative AI, because we've actually been on this path, on this progression, on this road for quite a long time. So we'll talk about how we've got to where we are right now. We're going to talk about language models and how they actually work. We'll talk about text-to-image models and get a bit of the intuition about how models can actually draw those images. We're going to talk about prompt engineering. This is an emerging field that as builders we really need to get across because it's going to play a big part in our futures. And then we're going to talk about where to from here, which is probably quite a foolish thing to do because things are moving so fast in this field all the time. But nevertheless, I'm going to give it a go. But first of all, we're going to talk about the road to generative AI. This is a path, as I've said, that we've been on for some time because we've been creating language, we've been creating content, we've been creating documents as society for obviously hundreds of years. And whilst all of that information has been written down, there are those amongst us who have tried to figure out how that language actually works. What are the relationships between the words in the documents that we make? And so that's where we start. We start with something called word embeddings. This is basically our target state. This is where we want to get to. We want to get to a numerical representation of language, of words on the written page. So we take all of the documents that we can get our hands on. We take the complete works of Shakespeare. We take all of Wikipedia and anything else that we manage to get from the internet. And we analyze that text to try and understand the relationships between the words in that text. And we assign numbers to those words. We can't just assign a single number. We have to have a whole list of numbers or a vector that we apply to these words so that we can then have a statistical relationship between words in language. Let me show you what I mean. I can only show you this in 2 dimensions, meaningfully, on this display anyway. So let's imagine that we've gone through as many different documents as we can get our hands on, and we've taken out each individual word and looked at its relationships with other words. And the first word we're going to look at is dog. Yes, it's that kind of presentation where we talk about dogs, and you can probably guess what the next word's going to be. But if we map out dog in a 2-dimensional vector, in its 2-dimensional space, based on our understanding of the word and its context with other words, well, I mean, at the moment, we're just going to place it here. It's on its own. It only really makes sense when we bring in another word. And so we bring in cat. And so cat has some kind of relationship with dog. We can all probably figure out how and why. So in these 2 dimensions, dog and cat cluster together. Now, if we look at other words like car, well, car is an interesting word in its own right, but it doesn't really have anything to do with dog or cat. So in our vector space, in our two-dimensional space of word mappings, of word embeddings, we're going to have that word further away from dog and cat. But if we were to introduce a word like bus, well, guess what? That's quite close to car because I guess they're both forms of transport. And when we go through all of the words that we can get our hands on, and of course this is just a subset of those, you can start to see these sort of spatial representation, again because we're in two dimensions here, but you can see the relationships between different words and how they exist in this word embedding space. And so this is where we want to get to. We want to get to the place where we have a vector that represents all of the words that we have in our language. And when we do that, we end up with something called a language model. That's all really a language model is. It's this vector representation of language, of words and their relationships with each other. And we're able to achieve that with various techniques, but in the past we've used things like word-to-vec. And so this was a very popular set of a couple of different kinds of algorithms where you could literally pass in all your documents and out would come a bunch of word embeddings, all of those vectors. And we were able to use these for various tasks that we call natural language processing. And these natural language processing technologies, these applications of this are quite familiar to us probably. We have things like text summarization, where we can pass in a large document, say an article, and get just a paragraph back. We can go for question answering. This is where we have a paragraph of text or a section of text. We know that the answer to a specific question is in there somewhere, and we can pose the question and get natural language processing to find that answer. We can do sentiment analysis, which is probably fairly straightforward, and speech language understanding. So this is the technology behind virtual assistants like Alexa, for example. So it's able to understand the intent of human speech through speech language understanding. And all of these are types of natural language processing, and all of these are powered by these language models, which are these lists of word embeddings. And we've been able to do this for quite some time. So let's talk now a little bit more about the generative side of the equation. How can we use this to generate more words? So we're familiar with the idea that we've got a sentence and we want to go for the next word completion in this case. So we've got a sentence here, but we actually can't see many of the words of this sentence. All we can see is the very last word in this sentence, which is lazy. And so we can take the word lazy and let's use a very simple word embedding. So one of the older word embeddings from back in the day where it can see, well, if I've got the word lazy, what is the word which is closest to lazy in the context of a sentence maybe that could make sense, that's going to complete this sentence? And the answer might be person, a lazy person. Does that make sense? Well, it does. That could work. That might be the word that we were after. But it's quite likely that it's not actually the word we want because we can't see the rest of the context. We can't see the rest of the words from the sentence. So if we're doing a simple word embedding vector space search, that's what we might come up with. How can we do better than this? Let's step in the direction of where we are today. And the next step after this sort of simple lookup was to use something called recurrent neural networks. And so recurrent neural networks were able to take not just the last word in the sentence, but the last few words in the sentence. So in this case, we can see Fox jumps over the lazy, and now we're looking for the next word. Now, I know that for many of you out there watching this, your squishy, organic human brain, which is actually incredibly sophisticated, can probably figure out what's happening here and can accurately predict what I ultimately want the last words to be. But put yourself in the space for a moment of a recurrent neural network who's been generating words, has generated fox, and has generated jumps, and over the lazy, and now it's trying to figure out the next word in the sequence. It's not got the full context of the sentence. Now, the reason for this is because recurrent neural networks are actually very resource hungry. So every extra word you add to that context exponentially increases the amount of compute power it's going to take to predict this next word. And so there is a limit to how big this context can be. Anyway, let's have a go. Let's use it and see what it comes up with. And it's come up with rabbit. Okay, does that make sense? Well, it kind of makes sense. I mean, there's a fox involved in the sentence, and foxes might jump over a rabbit. I suppose that could make sense. So it's given it the best go it can. What we really need in order to be able to properly answer this, what's the actual word that we're all looking for, is we need more context. We need the ability to be able to understand the whole sentence, if not the document that this sentence sits in. And in order to do that, we can use this technology called transformers. So back in 2017, so again, we've been on this road for a while. So back in 2017, this paper was released. It's from Google and the University of Toronto, and it's called Attention is All You Need. And this really is the birthplace of modern generative AI. This is where the vast majority of all of the innovation that you've seen happen over the last couple of years, and certainly the last few months, has come from work that has been built on top of this. Because this paper introduced the idea of the transformer architecture. And here is the transformer architecture. It's essentially a connection together of multiple different matrices, calculations, and neural networks. And we don't need to get into the details of exactly how this works. But there are a couple of really key things that this architecture allows us to do, which we weren't previously able to do with things like recurrent neural networks or any of the other technologies that came before it. And one part of that is the ability to apply what we call attention. It's in the title of the paper as well, right? Attention is all you need. It's attention to the language and the words that came prior to the word that we're currently trying to predict. So instead of literally just taking the last 5 words, 6 words, whatever it is, like we did before, we can actually look at all of the words that came before, but only apply attention to the ones that matter. What is this document actually about? What is the intention of this document? What's the style it's been written in? We can understand that through this method of attention. And the way this model works is for all of the context, so all of the sentence in our case, to be added in parallel, so all at the same time, rather than sequentially with our recurrent neural network. And this parallel processing can look at all of the language and figure out which parts of the sentence matter most and apply most to this word that I'm trying to predict at the end. So, in a nutshell, this transformer architecture, it's pivotal to how we have been able to make the leaps forward in generative AI. And the significant reasons for that are this notion of attention and the ability to parallel process vast quantities of data and make much larger models. Okay, let's go back to our example and now use a transformer-based network to come up with the answer. And now we can see the entire sentence. The quick brown fox jumps over the lazy, all together now, dog. Okay, so this is actually quite a common sentence, and so it's likely that the transformer-based network has been trained on this sentence and probably even knows that this is the right answer. Beyond that, it can probably even put it in even more context and say, actually, this is a bunch of typing tips, and this is an English language pangram, a sentence that blah, 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 blah. And so it can fill out all of this extra context. It knows, or it is capable of generating all of this extra data around the sentence that we have. A significant leap forward, not just for the Fox, but for language models as well. And so this is what we call a large language model, because it's trained on vast quantities of data and it's capable of doing some pretty remarkable things. So far, we've talked about language models, and we understand that they are these embedding vector spaces of words. Large language models, what's the difference? Well, really, the main difference is they're larger, and it's the transformer architecture models that have allowed us to do that. Now let's take a look at what's happened kind of over the last few years. We've been building these transformer-based architectures and putting more and more data into these models. And as we do that, what we've seen is that the subjective performance of those models, like how quote-unquote intelligent they are, just continues to grow. And this is a very interesting thing for us to observe. In machine learning in general, the more data that we pile into models, generally the better they do, but to a point. And a point is reached at which we add in more data, and then it kind of all falls in a heap, and we have to iterate on the design and try again. But with transformer-based architectures, well, that might happen, but it hasn't happened yet. And the more data that we put into these transformer architectures, subjectively, the better the models are becoming, and they are getting remarkably good. You've probably seen some of this for yourself, but they go beyond just purely understanding language to being able to reason and being able to simulate stuff as they're making predictions about, say, a physics experiment or mathematics. And they weren't that good at maths, and now they're kind of getting better at maths. They are not a calculator, but through language, they're able to understand how to perform increasingly more complex tasks. Now, are they alive? Are they sentient? No, they're not. But they are getting impressively capable. Something else interesting is happening here, and that's what does happen next. It is also the case that we are getting quite good at building much smaller models that have much better capability. So that is really what's been happening over the last few, weeks and a couple of months, is that models with in the teens of billions of parameters are now capable of performing just as well as some of these models with in the hundreds of billions of parameters. So this question mark of where do we go next from here is quite genuine. We absolutely will continue to go bigger, but we'll have more specialized and higher quality models with smaller numbers of parameters as well. And when we're talking about these models, which have, let's just review those numbers one more time. Look up at Bloom there with 176 billion parameters inside of that model. I mean, that's enormous. That's a lot of data. It took well over 100 days to train. It took many parallel compute GPUs to be able to train that model. So these things they're big models, and they're not the kinds of things that we're just going to, say, oh, it's a rainy weekend, I might build myself a large language model. That's not the way it works. Instead, what we have here are these foundation models. So Bloom is a good example of a foundation model, a general purpose language model that's been built at fairly significant expense, which is now available to us because Bloom is open source, and it's now available to us so that we can take that and apply it to our particular task or our particular need. Now, before we go too much further, I just want to talk about how relatively easy it is to get started with this stuff. And it's not just the case that you need to take a foundation model and start applying it to your particular need. You can also use tools around this as well. So let me mention quickly Amazon Code Whisperer. This is a generative AI tool that you can install inside of your IDE when you're writing code. And I have an example here of where I've used Code Whisperer to start helping me to create another machine learning model. And this is way more powerful than using code completion, for example, because it understands things like the variables and the classes that you've built beforehand, what libraries you've installed, and it genuinely is sort of pair coding. And so generative AI pair coding is absolutely a thing. If you're not using it, then I really, really encourage you, if you're writing any code at all, please take a look at the generative AI tools out there to help you write code, because they significantly improve your efficiency of writing. And I'll never not use these tools again. They are quite amazing. In addition to that, though, if you want to go ahead and start using foundation models, again, they're relatively easy to get your hands on. Inside of AWS, you can use SageMaker, and there's foundation models available inside of Jumpstart. So you can get started really quickly inside of SageMaker with foundation models. Okay, let's just recap then some of the applications for generative AI. So text generation, we've seen a couple of different types of that already. Anything really that you can turn your mind to, you can probably do it with generative AI. So whether it's writing children's stories, or whether it's writing blog posts, or whether it's writing scripts for presentations about generative AI. No, I didn't do that, but I probably could have done. Game design is using generative AI, both on the graphics side as well as the story narrative side, and generating different characters for the games. Industrial design's been using generative AI for some time. Drug design research, this is really exciting. It's a little bit outside of my area of expertise, but imagine that instead of taking a whole bunch of language documents, so Wikipedia and all that kind of stuff, imagine we take the designs for drugs. So there is some kind of textual representation for the recipes, is that the right word, for how drugs are put together, and we understand what those drugs do. Now can we use generative AI to design new drugs, or point us in a direction of the next big breakthrough? That's super exciting. And then we have image generation, so the ability to take a text prompt and generate an image from that prompt. Let's take a look at that in a little bit more detail and think about it from an intuition point of view. How does that even work? Because it seems magical to me anyway. First of all, we've got language models, and we've already sort of talked about that, and we've got our word embeddings. We understand essentially how we can codify language into this language model, this word embedding space. Well, we can take the same techniques and we can do the same thing with images as well. So instead of having some words, we've got a group of pixels, and this group of pixels looks like a certain thing. So we're able to map that into our image embeddings model. And if we mix both of those two things together in an application, then we can come out with a text to image application, or text to image model, such as Stable Diffusion. So let's take a really quick look at this. Stable Diffusion is an open source text to image model which can do some pretty cool stuff. Now, what we're looking at here are 4 images that Stable Diffusion did not make. These images are actually real photographs of Marigold the puppy, who I have to say, even though this was a few weeks ago, that she's a lot bigger than that now. But anyway, these are 4 images of what Marigold the puppy used to look like. And what we're going to do in this example, because you've probably seen many times, prompts and text to just random images. Now we're going to create images of Marigold the puppy, and we're going to tune Stable Diffusion. We're going to train Stable Diffusion to use these images. So we can pass these images into Stable Diffusion and then put in a new prompt, such as this one, a photograph or photo of Marigold the puppy as street art. And Marigold the puppy's never been street art, I'm sure of it. And so this is entirely a generated image. You can kind of see that this looks like a pastel image or something of Marigold the puppy drawn on the street with some people in the background looking at it, probably fairly bemused. Let's have another go. This is a photo of Marigold the puppy as 8-bit art. And so you can see it's kind of pixelated there. I love this. And actually, as I look back on this, it says a photograph of Marigold the puppy is 8-bit art, which is a bit of a funny way of doing it. And then you look at it and you go, actually, do you know what it is, isn't it? You can see a kind of shadow under there. This is an art piece hanging on the wall somewhere. It's a photograph of exactly what I asked for, which is pretty amazing stuff. So how does Stable Diffusion generate an image like this? How does it draw images? In the past, we used to use things called generative adversarial networks to try and find their way very slowly to be able to draw an image. Two neural networks that were sort of working off of each other in competition with each other to generate data. The problem with that was it was big, unwieldy, and often quite unstable, and so would sort of fall in a big heap and you'd have to start all over again. And so the name Stable Diffusion kind of says it all. Stable diffusion, it's a way of using diffusion in quite a stable way to create images. Let's dive in a little deeper than just the name, and let's take a look at the sort of the intuition for how it draws these images. So here is an input image. So this is an actual image, and we're going to use this to train Stable Diffusion in the first place. So this is not the fine-tuning. This is training it in the first place of how to draw images, realistic looking images of Marigold the puppy in this case. And what we do is we add a small amount of noise to that image, to the original image, and we train a machine learning model to remove that noise from the image to get back to the original image. So nothing too incredible at this point, something that a Photoshop plugin could probably do, a denoiser. It turns out that it's not that hard. I mean, a neural network can get to the point where it can remove the noise and get back to the original image. So that's good. So then we take that neural network and we continue to train it like that. We add a little bit more noise and then get back to the point where we've got a bit of noise, and then run it again and get back to the point where we've got no noise. And we repeat this over multiple different stages and different steps until we get to a point where we've got a model which is going from completely noise all the way back through these stages, back to a point where it's actually found an image of a dog. And it might not be the original image it started from, it might draw a new image. And so this is my representation of what that might look like. This is actually another photograph of the dog, but you get my point. It's managed to train itself up so that it can go from random noise all the way through, gradually removing stage by stage by stage, and you come up with this new image. And that's what's happening behind the scenes of Stable Diffusion. And that's how we're able to create images like this, which is Marigold the puppy on a space station. And it's not happened yet. I can guarantee you that's not a real image. Maybe it will one day. Who knows? Now let's take a look at this statement here, Marigold the puppy on a space station. This was the prompt that I used to create that image. And what I now want to talk about is prompt engineering, which is an emerging field and something that we as developers and builders and technologists of all kinds need to work on this, and we need to understand this because we're going to be using this a lot over the coming years. That's my prediction anyway. Let's take a look at an example of how we could use prompt engineering in a language setting. Let's say, for example, that we're going to create an application. It's going to use generative AI to write blog posts for us, which I'm sure is happening already. And so here's a simple little quick app. We can type in a title of what we want the blog to be about, the topic, and maybe we're going to put in there how long we want this to be as well. So not a lot of information. In reality, we'd probably have a little bit more than this. But what happens when we take that and we then want to go and use a generative AI algorithm to create our post for us? Well, what we do in the background is we'll end up putting all of those bits and pieces of information about the blog into a prompt. So a prompt is just a text string. It's just a piece of language in a string which says what we want to happen. And so what I want to point out here is that the prompt is actually much longer in this case than simply the information we've collected from a user. So we have this part at the top which explains, you're a journalist for whatever you are and how to write the article. More information than just the title and the topic. This becomes part of the intellectual property of this application, how these prompts work. And there are actually already marketplaces for people who are selling prompts for various generative AI platforms. Incredibly enough, they are just text strings. This is the kind of thing that we're going to have to get used to. And what I'll present for you today is that this is really a new way to program. Imagine that I wanted to create a chatbot that used generative AI to, talk to support requests at my organization, for example. What do I do? Well, do I go into Python and start writing code that looks like this? Create myself a chatbot, tell it what the lengths of the average replies got to look like, that I want it to be friendly, that the bot's going to be called chatbot, etc., and what the topic is. Well, no, that's not what we're going to do. That's not how we create the chatbot. Instead, what we do is we pass a prompt into a large language model, and it might look a little bit like this. So this is a friendly and safe chat session between a user and a computer called chatbot. And then start to put in some examples. So these are still parts of the prompt. We can start to put in some examples of where we want to go with this conversation. Examples so that the language model understands the cadence, understands that the user asks a question, the chatbot answers the question. This is a way to do it, and this is what the prompt might look like. And so this is prompt engineering, and I'll certainly have more presentations on this in the coming weeks and months ahead. All right, let's talk about where to from here. Probably quite a foolish thing to do because, as I said before, as the weeks go by, as the days go by, honestly, I wake up each morning and just look to see what new papers have been written so I can see where we're going next. But generally, where to from here? Well, as I said before, models will keep getting bigger and they'll keep getting more subjectively sophisticated. They'll be able to do more and more impressive things. Now, in addition to that, sort of open brackets, models will also get smaller and more sophisticated too. But in many ways, those smaller models are supported by the larger models and the development of the larger models. So both of these things are going to be true, but the bigger models are probably something to keep an eye on. Many developers, so people like you and I, are going to be working on foundation models that other people have been created. We're not going to create our own foundation models in most cases. We're going to take foundation models that have been produced and we're going to do things with them. We're going to apply them to our specific tasks and our specific needs. We're going to fine-tune them. We're going to learn how to use prompt engineering to get the best out of them. That's where we're going to spend quite a bit of our time. Now, training costs and sustainability definitely come into focus. This is very much a hot topic for lots of people in the industry. Now, the training costs are often about the training of foundation models. So again, not something that we necessarily going to be directly involved in, but it's still important for us to know about it because, of course, with the cost comes energy use, and that's where sustainability in that conversation comes in. Now, there are people that are working on algorithm optimization. Building those smaller models is an example of that. And there are dedicated hardware designs now that are designed specifically for large language models, which we can use. They reduce costs, and they reduced costs because they take less power, which works into that sustainability conversation. The other thing that is worth talking about as well is the inference costs. So the story here is basically exactly the same, but the location of where this happens is different, right? So we're not going to be training foundation models, but we are probably going to be hosting inference or hosting models for inference. And so we also need to take into account how can we optimize that? How can we prune the models down? How can we quantize the models down? All those types of things. And are there dedicated hardware that we can use, again, to bring down the energy consumption, bring down our costs, and do the right thing from the point of view of sustainability? At Amazon Web Services, there's essentially a multi-pronged approach to generative AI. You may have seen the Amazon Bedrock announcement quite recently. We also have the dedicated hardware for both the training and the inference side of these large language models, and also Amazon Code Whisperer. As I pointed out before, even if you're not going to be working deep in machine learning, take a look at pair coding, generative AI pair coding. You will not regret it, and it will make you way more efficient in the generation of your code. Amazon Bedrock was announced fairly recently, and this will be a serverless environment where you can fine-tune and make inference with large language models without having to get into the weeds of how to actually host these models yourself. A number of launch partners have been announced, and Amazon will have their own large language models available as well through Amazon Titan as part of Amazon Bedrock. In addition to this, and if you want to get going now with any kind of generative AI or machine learning inside of Amazon Web Services, take a look at Amazon SageMaker Studio Lab. This is an entirely free environment. You can use a Jupyter Notebook environment. You can have access to GPU. You can put your own code in there. There are code examples that you can use in there. You can use it for generative AI. Some of the images that you saw earlier on in this presentation created with Stable Diffusion. Stable Diffusion can also run inside of your SageMaker Studio Lab environment completely for free. We've also got inside of SageMaker, we have Jumpstart. Jumpstart is a hub with hundreds of open source pre-trained models that you can deploy really quickly and start to use in your project. And this includes generative AI. And those foundation models are in there too. So you can use the foundation models such as Bloom and launch them inside of your account, even with just a single click. So that's Amazon SageMaker foundation models. Thank you so much for taking some time out to talk about generative AI with me. If you've got any feedback about this, then please do let us know. Take a look at this QR code or follow this link to provide us with some feedback. Thank you. My name's been Mike Chambers. If you want to reach out to me on social media, then please look for me at Mike G. Chambers. LinkedIn's probably the best place. Happy to have a conversation with you there. And until the next time, thanks for watching.